One of the most interesting, but perhaps less known spacecraft in history is something called Pioneer 10. It was launched from Earth in 1972, the same year that astronauts last walked on the moon. And it went out to the outer planets. It was the first man-made object to leave the solar system. Its mission was very modest. It was designed primarily to traverse the asteroid belt between Mars and Jupiter. Kept going, got to Jupiter, and took some images of Jupiter, found the red spot, took images of the great red spot, which people still are puzzling over what causes that. And it kept going beyond Jupiter and is now out of the solar system, headed toward distant stars. It's something like 10 billion miles away, which is quite a distance. It's sort of, in a way, like I say, the pioneer of all deep space probes. We've had Cassini, New Horizons, Galileo, all of these, Voyager, all of these things that followed really are following in the footsteps of Pioneer 10. So Pioneer 10 did not have a whole lot of capability compared to what has come later, but it really blazed the trail that they're all following.
Let's now consider the idea of escaping Earth altogether and traveling to another planet. How long will it take to get there? What is the best route to take? Will humans be able to survive en route? The answers to these questions are critical for successful travel to other planets and moons in our solar system. In fact, some even say that successful interplanetary travel is essential to the long-term survival of the human race. Let's explore the fundamental physical limits that govern interplanetary space travel. First, let's toy with the idea of a very economical way to get to Mars, if we don't care about how long it will take to get there. It's important to recognize that the single biggest cost to a space mission is the change in velocity required, or delta V. Getting somewhere in space is all about the increase in kinetic energy, rather than a change in altitude. And a higher delta V is going to require more fuel. And more fuel will increase the mass of the system that is launched into space. So one fuel-efficient maneuver is termed the gravity assist, or slingshot maneuver. A gravity assist trajectory brings a spacecraft on an interplanetary trajectory within the gravitational field of an intermediate planet, whose gravity field changes the trajectory and speed of the spacecraft. Now, you may be thinking to yourself, how can the spacecraft be accelerated without violating the fundamental laws of conservation of momentum and conservation of energy? That's a great question. Thankfully, a gravity assist maneuver still abides by these fundamental laws. So if conservation of energy holds true, where does that extra kinetic energy come from? Well, the energy of the intermediate planet actually decreases, but ever so slightly. But with a vanishingly small decrease in energy of the main planet, it turns out that the energy gained by the spacecraft can be huge. The best way to conceptualize a gravity assist is by a basic, albeit crude, analogy. Imagine that you're standing on the edge of a road and throwing a small, lightweight rubber ball towards a moving truck. Let's assume that the ball collides with the front of the truck in a head-on collision and bounces straight back. If you throw the ball at 10 miles per hour towards the truck, and the truck is moving towards you at 45 miles per hour, how fast will the ball come back to you? Well, this can be analyzed by applying the conservation of momentum and the conservation of energy. Also, we need to assume that there is a perfectly elastic collision of the ball with the truck, that the truck is much more massive than the ball, and that the ball bounces back in a purely one-dimensional direction. While you have thrown the ball at only 10 miles per hour, the driver of the truck going at 45 miles per hour sees the ball coming at him at 55 miles an hour. So with a perfectly elastic bounce, the driver would see the ball rebound at a speed of 55 miles an hour away from him as his truck continues to move forward. Then, when we take that 55 mile an hour rebound speed and convert it back to your frame of reference, the rebound speed is 100 miles per hour. So the truck, with its very high momentum, imparted a lot of momentum to the rubber ball. By analogy, we see that the large planet lends some of its momentum to the spacecraft. The trajectory of the spacecraft can be planned such that it approaches the planet from behind, and the planet's gravity will pull it along, redirecting its trajectory and adding kinetic energy to the spacecraft. The amount of extra velocity imparted to the spacecraft depends on the velocity of the spacecraft, the velocity of the planet itself, the approach angle, and how much the trajectory is deflected, which depends on the gravitational field of the planet being flown by. As an example, let's consider a spacecraft approaching Jupiter for a gravity assist flyby. When we consider the dynamics from the frame of reference of Jupiter, the oncoming speed of the spacecraft on a hyperbolic trajectory is the same as the departing speed at an equal distance away from Jupiter. This is analogous to the truck driver seeing the rubber ball rebound from his windshield at the same speed at which it approached, but in the opposite direction. However, if we shift to a heliocentric or inertial frame of reference, we now need to add in Jupiter's velocity as it rotates in its own orbit around the Sun. This is done by constructing velocity triangles, where we arrange the spacecraft's velocity vector and Jupiter's velocity vector head to tail to form a triangle. The resultant of this velocity triangle is the spacecraft's velocity vector in the heliocentric frame. And now, by comparing the length of these vectors, we see how it's possible to dramatically increase the kinetic energy of a spacecraft. This added energy is very useful for getting the delta V needed to make it to distant planets. So how practical is this? The gravity assist maneuver will typically add some time to a mission due to the relative alignment of the planets, so it isn't very practical for human-carrying interplanetary flight. But for robotic spacecraft, it's very common to rely on the gravity assist maneuver since the energy is basically free. For example, each of the Voyager probes relied upon gravity assists to work their way through the solar system. Voyager 2 performed flybys of Jupiter, Saturn, Uranus, and Neptune, making observations of each planet along the way, and relying upon a gravity assist with each flyby. And now, both Voyager probes continue to function on interstellar missions beyond our solar system. Another interesting use of the gravity assist was by the Galileo probe, which was designed for a mission to study Jupiter. The initial mission design was for Galileo to follow a direct trajectory to Jupiter via Hohmann transfer, relying upon a liquid hydrogen booster stage. Following the Challenger disaster, safety concerns prevented the launch of this booster on board the planned shuttle mission. Galileo's mission designers then went back and developed a new gravity assist trajectory that took the spacecraft on flybys of Venus, back to Earth a second time. Galileo gained 2.2 kilometers per second when passing Venus, another 5.2 kilometers per second on the first Earth flyby, and finally another 3.7 kilometers per second on the final Earth flyby, for a total delta V of 11.1 kilometers per second, for free. Well, almost for free. The cost was an extra time for the mission, which led to failure of some of the onboard systems, such as the primary antenna. And the extra kinetic energy came from the host planets that were flown by. So Earth sacrificed some of its kinetic energy, slowing down ever so slightly by a total of 4.3 nanometers per second. Not a big deal. Now, what if we want to get our spacecraft there a little faster, rather than just contentedly coasting along with the free rides that we get from gravity assist? We could continue to fire rockets throughout the journey, but that would be incredibly expensive in terms of fuel requirements. Instead, there's an interesting, highly efficient propulsion concept available for sustained acceleration: electron-ion propulsion. First used on the Deep Space One probe during 1998 to 2001, the main idea of an electric ion thruster is to create ions in a propellant, typically by hitting them with an electron beam. These ions are then accelerated through an electric field to an extremely high exhaust velocity of around 50,000 meters per second, almost 112,000 miles per hour. The acceleration of each ion produces a small amount of thrust due to the change in momentum of the ion. The beauty of ion propulsion is that it requires very little propellant. So even though the thrust production is not very high, the mass flow rate of propellant is extremely low, giving amazing values of specific impulse. For example, NASA's Dawn spacecraft, launched in 2007, carried on board 3 redundant NSTAR ion thrusters to take it on a scientific mission to study asteroids beyond Mars. Each thruster was capable of producing a mere 90 millinewtons of thrust. But the total propellant mass for this 9-year mission was only 425 kilograms, and the power requirement was only 2.3 kilowatts. Now, it may seem like it would be impossible to do anything meaningful with only 90 millinewtons of thrust, which is about 2/100ths of a pound, just a puff of thrust. However, this propulsion system was capable of increasing the Dawn spacecraft's velocity by 10 kilometers per second, over 22,000 miles per hour, which is the highest velocity increment ever achieved by continuous thrust. The secret is to accelerate at a snail's pace. One way of looking at it is that it can go from 0 to 60 miles per hour in 2 days, and from 60 to 120 miles per hour in 2 more days, and so on and so on. At the same rate of acceleration, it takes 2 years to reach full speed. So the key enablers to this impressive acceleration are high specific impulse and the luxury of time. Because ion thrusters produce so little thrust, they are only practical in space, outside the reach of atmospheric drag. The NSTAR thruster has a specific impulse of up to 3,160 seconds, which is about 7 times higher than that of the Space Shuttle's main engines. And with a total mission duration of 9 years, there was plenty of time to fire the ion engine and achieve that acceleration. The technical challenge, then, is wear and tear on the ion thruster during continuous operation. Based on this impressive propulsion capability, the Dawn spacecraft became the first ever to orbit 2 separate extraterrestrial bodies in the asteroid belt, conducting meaningful science along the way. The spacecraft carried on board high-resolution cameras, which provided incredible insight into the terrain of Vesta and Ceres, the 2 asteroids, from an altitude as low as 210 kilometers from Vesta's surface. Now, the path that the Dawn spacecraft took to reach these 2 asteroids is fascinating. And this is a key point. The best path from Earth to the asteroids was not a direct straight line. Instead, following launch from Earth in September 2007, Dawn headed for Mars. It took an outward path from Earth, rendezvousing with Mars on February 17, 2009, at an altitude of only 549 kilometers, or 341 miles. Then, using this brief encounter with Mars as a gravity assist, Dawn continued to accelerate until its rendezvous with Vesta in July 2011, when it entered into Vesta orbit. It stayed in various orbits around Vesta, collecting scientific data for over a year, until departure on September 2, 2012. Then it flew for another 2.5 years before reaching Ceres in March 2015. It then remained in Ceres orbit, acquiring scientific data for the remaining lifetime of the spacecraft. This interplanetary trajectory is truly impressive. The speeds involved are incredibly high, and the timing of the propellant burns must be precise. Otherwise, the spacecraft can easily miss a rendezvous or crash into the surface. So it turns out that the gravity assist maneuver is highly useful for robotic space probes, where we aren't too concerned with how long it will take to get to the destination. By contrast, human-carrying interplanetary travel is deeply concerned with the length of the mission, due to the many life support requirements. So a manned mission needs a much faster route. We can take a Hohmann transfer between Earth and Mars as a relatively straightforward and reasonably fast trajectory to Mars. And it's the trajectory that requires the least amount of fuel, since the burns to enter and exit the elliptical transfer trajectory are parallel to the orbits of Earth and Mars. Let's look at this path to Mars in some detail. In order to have reasonable fuel and time requirements for the Martian journey, we need Earth and Mars to be reasonably close to one another in their orbits around the Sun. But the distance between the two is changing all the time. Since Mars is much farther away from the Sun, with higher potential energy, its orbital speed is much slower than Earth's. The period of the Martian orbit is 684 Earth days, which of course, Earth's period is 365 days. Because of this difference in the period of their orbits, there is a beat frequency that describes the distance between the 2 planets. The period of this beat frequency, called the synodic period, is 26 months. The implications of this synchronization are huge. It means that a successful trip to Mars, or a return from Mars, with reasonable energy requirements can happen only about every 2 years. For example, the first 2 unsuccessful Soviet attempts to send a flyby to Mars were in October 1960. More unsuccessful attempts occurred 2 years later, in October and November of 1962. And the first successful flyby, which was Mariner 4 from the US, launched 2 years after the second Soviet attempts, in November 1964, and so on. Mariner 6 and 7 launched in spring 1969, Mariner 8 and 9 in spring 1971. Summer 1973 saw 4 unsuccessful attempts by the Soviet Union, and in 1975, Viking 1 and 2 left for what became the first successful landings on Mars. On top of that, due to the variations in eccentricity of the Earth and Mars orbits, there are substantial differences in the distance of that closest approach that happens roughly every 2 years. The period of the longer timescale variation is 15 years. At their closest approach, the distance between Earth and Mars ranges between about 60 million kilometers and 100 million kilometers, depending on where we are within the 15-year cycle. Clearly, we'd prefer to travel that 60 million kilometer distance, but it may not be feasible to wait 15 years if we've just missed it. The 2-year and 2-month wait for the next launch window for the closest approach is long enough. Now, so far, we've been ignoring a key aspect of how to analyze the trajectory when several gravitational bodies are involved. Our analysis so far has been limited to the 2-body problem, which, for example, would be Earth and the spacecraft. But for a spacecraft traveling to Mars, we actually have a 4-body problem, with the gravitational fields of Earth, Sun, and Mars all interacting with the spacecraft. The N-body problem is a notoriously difficult problem to solve in mathematics, so we need to resort to some approximations. The most straightforward approach is to use a patched conic approximation. This involves breaking the problem down into a series of 2-body problems, where the spacecraft interacts with one large body at a time. The solution for each 2-body problem, which is some form of a conic section, is patched together in order to piece together a meaningful trajectory. So, for example, a spacecraft going from Earth to Mars will first need to depart Earth orbit via an appropriate hyperbolic trajectory. Then the spacecraft follows an elliptical trajectory from Earth to Mars, with the Sun residing at a focus of the ellipse. Finally, the spacecraft will enter Martian orbit via a hyperbolic entry trajectory. Now, how do we decide where to draw the boundaries between these separate solutions? It depends on the relative influence of a planet's gravity versus the Sun's gravity. We can determine this by calculating a sphere of influence for each planet, which represents the radial extent where a planet's gravity will dominate the spacecraft's trajectory, rather than the Sun's. We can think of it as the boundary of a planet's gravity well. We can anticipate that the more massive a planet is, the larger its sphere of influence will be. And we can also anticipate that, for a given size planet, the closer it is to the Sun, the smaller its sphere of influence will be due to the increasing gravitational influence of the Sun. Bringing these factors together, the radius of the sphere of influence is equal to the semi-major axis of the planet's orbit times the ratio of the mass of the planet to the mass of the Sun raised to the 2/5 power. For example, the radius of the Earth's sphere of influence is 925,000 kilometers, which is 575,000 miles. This sphere of influence is more than twice the distance from Earth to the Moon's orbit, and it is 22 times the radius of the orbit of a geostationary satellite. While that radius may seem large, it is just 0.6% of the distance from the Earth to the Sun. Now, for a journey to Mars, the radius of the Martian sphere of influence is 577,000 kilometers. So at their closest approach distance of 50 million kilometers, the Earth's sphere of influence accounts for only the first 1.5% of the journey, and the Martian sphere of influence accounts for less than 1% of the distance. Now that we've divided the journey into these 3 segments, we can do some basic analysis of the journey. The main objective here is to determine how much total delta V is required to get to Mars. This is one of the primary design drivers for the mission, since propellant mass directly depends on the fuel burn required to achieve that delta V. Before we jump into this brief analysis, it's absolutely critical that we keep in mind the various frames of reference that we're dealing with. For the portion of the trip dominated by the Sun's gravity, we're of course in the Sun's frame of reference, which we can consider an inertial frame. However, when we compare orbital parameters for Earth escape or Martian orbital capture, the analysis will be in the Earth or Mars frames of reference, respectively. But in order to match the velocities that we find with the interplanetary trajectory, we must transform these velocities into the Sun's inertial frame of reference. That is, we must account for the motion of Earth around the Sun when patching between the Earth's sphere of influence and the Sun's. Let's start with the heliocentric problem first, which is about 97.5% of the journey. So for this phase, we're ignoring the influence of Earth and Mars, leaving us with a two-body problem of the spacecraft and the Sun. We'll assume a Hohmann transfer from Earth orbit to Mars orbit, where the semi-major axis for the elliptical Hohmann transfer is the average of the orbital radii for Earth and Mars, which is about 189 million kilometers. Now, the energy of the transfer orbit is higher than the energy of Earth's orbit around the Sun, because its semi-major axis is so much larger. That is, the average distance of the transfer trajectory from the Sun is much larger than the radius of Earth's orbit. And our spacecraft will enter the transfer orbit at the location of perihelion, or the point along the trajectory that is closest to the Sun, where it will have maximum kinetic energy. And at this same point, the radius of Earth's orbit is the same as the perihelion radius of the transfer orbit. So if the total energy of the transfer orbit is larger than Earth's, our spacecraft enters that elliptical trajectory at the point of highest kinetic energy, then we know the spacecraft must be traveling faster than Earth. It turns out that the Earth orbits the Sun at a speed of about 29.8 kilometers per second, and our spacecraft must be traveling at 32.72 kilometers per second, or 2.94 kilometers per second faster than Earth at perihelion of the transfer orbit. And of course, the spacecraft must be traveling in the same direction as Earth at the point of transfer orbit entry. This will give the spacecraft sufficient kinetic energy to enter the transfer orbit. After traveling all the way through half a period of the elliptical transfer orbit and reaching Mars, the spacecraft will be traveling slower than Mars. This is because the Mars orbit has higher total energy than the transfer orbit, and the spacecraft is at the point of aphelion at the time of Mars rendezvous. So our spacecraft has to arrive at the Martian orbital path just before Mars arrives, so that Mars can catch up with the spacecraft and pull it into its orbit. Mars revolves around the Sun at a rate of 24.14 kilometers per second, and the spacecraft on the Hohmann transfer will arrive with a velocity of 21.49 kilometers per second, which is 2.65 kilometers per second slower than Mars. Thus, the velocity of the spacecraft relative to Mars at the point of orbital capture is 2.65 kilometers per second. We now need to come up with hyperbolic trajectories at Earth and Mars that will get the spacecraft traveling in the right direction and at the right speed. These are defined by the patch points between the hyperbolic conic sections for Earth and Mars. To summarize, at Earth we need a velocity that is 2.94 kilometers per second away from Earth at the edge of Earth's sphere of influence, oriented in the same direction as Earth's velocity vector at the point of perihelion. And at Mars, we need a velocity of 2.65 kilometers per second towards Mars on a trajectory parallel to the Mars orbit. The total energy of the Earth escape hyperbolic trajectory will be composed of the kinetic energy of the spacecraft at the edge of the sphere of influence, since the potential energy there is approximately zero. With that known value of energy, we can find the required kinetic energy at a much lower altitude parking orbit around Earth, where the potential energy is less. If the parking orbit has a radius of 6,697 kilometers, or an altitude of 326 kilometers, then the orbital speed is 7.71 kilometers per second. But the required hyperbolic trajectory at that altitude requires a velocity of 11.3 kilometers per second. So the difference between the two, 3.59 kilometers per second, must be supplied by an appropriate burn while in the low Earth parking orbit. This single burn is enough to carry the spacecraft all the way to Mars rendezvous. Once the spacecraft gets to Mars, it will be arriving on an elliptic trajectory around the Sun, at the aphelion of that orbit. It will also be on a hyperbolic trajectory relative to Mars, transitioning between the two trajectories at the edge of the Martian sphere of influence, where we already found that the velocity of the spacecraft towards Mars needs to be 2.65 kilometers per second. As the gravity of Mars captures the trajectory of our spacecraft, its potential energy goes down and the kinetic energy goes up. This continues until the spacecraft is at the closest point to Mars on the hyperbolic trajectory. If the spacecraft did nothing at this point, it It would continue on around Mars and continue away from the planet on its hyperbolic trajectory. This would be a gravity assist maneuver. Instead, if we want to capture a Martian orbit, the kinetic energy of the spacecraft must be decreased via a retroburn to slow down. For a 3,580 kilometer radius parking orbit at Mars, the spacecraft will have a velocity of 5.57 kilometers per second on the hyperbolic trajectory. However, a circular orbit at that altitude requires a velocity of 3.47 kilometers per second, a difference of 2.1 kilometers per second. Thus, the spacecraft must perform a retroburn to decrease its velocity by 2.1 kilometers per second at the point of closest approach to Mars. Now we have the total delta V burn to go from a parking orbit on Earth to a parking orbit on Mars. 3.59 kilometers per second to leave Earth, and a second burn of 2.1 kilometers per second at Mars for a total of 5.69 kilometers per second. So how much propellant mass does this take? Well, if we have a specific impulse of 350 seconds, then the initial mass of the spacecraft must be 5.25 times more than the final mass of the vehicle. That's actually a pretty huge fraction of the mass devoted to propellant. So for every kilogram of mass that we wish to deliver from Earth to the parking orbit in Mars orbit, it takes 4.25 kilograms of propellant to conduct the 2 required fuel burns. Okay, so now we know how to get to Mars. But how long will it take to get there? We can determine this by calculating half the period of the elliptical orbit associated with the Hohmann transfer trajectory, since our spacecraft only takes the outbound leg. This time of flight depends strongly on the distance that must be traveled. It's equal to pi times the square root of the cube of the semi-major axis of the transfer ellipse, divided by the Sun's gravitational parameter. For our transfer from Earth to Mars, the semi-major axis is 188.7 million kilometers, which gives a time of flight of about 8.5 months. Can you imagine being cooped up in a spacecraft for 8.5 months? Isn't there anything that we can do to shorten that journey? Well, there are other trajectory options available to get to Mars, but all of them will require more fuel burn and more propellant compared to the Hohmann transfer. However, no matter what we do, it's going to be a long journey. And once humans make it to Mars, they're going to have to wait a long time before the next launch window arrives for any possibility of a return to Earth. So what are the risks that humans will have to endure throughout a long journey to Mars? And will it be possible to set up a permanent human settlement on Mars? The challenges are daunting, but the opportunity is tantalizing. So how can a permanent habitat be built on Mars? It's highly desirable to minimize the amount of material that must be launched from Earth up to Mars due to the huge fuel requirements of over 5 kilograms of propellant for every kilogram of payload. The innovative alternative is to fabricate living spaces in situ from the raw materials available on Mars. For example, the Martian regolith has all of the raw ingredients needed for making glass, including sodium dioxide, sodium oxide, calcium oxide, and aluminum oxide. Mars is a surprisingly benign living environment. Despite the lack of oxygen in the atmosphere, there is ample carbon dioxide, 95%. And we're learning that there is ice water on Mars, perhaps even a lot of subterranean ice. There is even evidence of liquid water in some places. So we have carbon dioxide, water, and sunlight, the necessary ingredients for plant photosynthesis. This opens up huge opportunities for growing food and all of the other benefits that plant growth provides. On the downside, however, there are the harsh impacts of the space environment. First, there's the microgravity of the long transit flight, and Mars's reduced gravity that is only 38% of Earth's. This weightless or reduced weight environment has long-term impacts on the human musculoskeletal system. If bones are not carrying a load for an extended period of time, they become brittle due to decalcification. Also, muscular tone deteriorates over time due to underuse. Thus, astronauts in space for extended periods must conduct rigorous exercise regimens on specialized treadmills and bungee contraptions that induce loading on the astronaut's skeletal system. Also, since buoyancy principles are no longer at work without gravity acting on fluid within the body, there is a redistribution of fluid within human tissue. Fluid that normally pools in the legs is distributed throughout the rest of the body, causing the kidneys to work harder to remove what is sensed as excess fluid. Over time, this results in a reduction of plasma volume by up to 20%. And vision can also be degraded. The other huge risk of space is solar radiation. There is persistent radiation from the sun and from galactic cosmic rays, which terrestrial humans are normally shielded from by Earth's atmosphere and magnetic field. However, in space, there is insufficient shielding to block these high-energy particles, leading to much higher exposure levels. This effect can accumulate over a long-duration flight, such as a trip to Mars, leading to long-term health hazards. Beyond the cumulative effects, though, there is also the danger posed by the sudden release of intense radiation from a solar flare. These solar flares are mildly disruptive on Earth, causing increased ionization in the ionosphere, leading to disruption in various telecommunications. But in space, the radiation from a solar flare can even be deadly due to the acute radiation exposure. So long-term habitats in space, or interplanetary spacecraft, will have to have at least a portion of the spacecraft or habitat equipped with a radiation-hardened shelter, with enough shielding in place to protect the astronauts from intense periods of radiation. In the meantime, robotic spacecraft offer opportunities for telepresence and remote-controlled missions that are allowing us to explore the solar system as never before.